Okay, so till the last class we have understood. Till the last class we understood this part, the term symbols for diatomic molecules. We discussed this, and I also gave you an assignment to complete this part. The questions as it appears on the screen, and additionally, one O2 plus molecule should also be considered while you are making all these things. So that was the okay, and after that we had a detailed discussion in last two classes about the selection rules, the conservation of angular momentum, including the photon's angular momentum, which gives us three rules. These three rules that we see on screen. Okay, so change in orbital angular momentum, change in spin angular momentum, and change in the total angular momentum. All these three things are governed by the three rules as given here, already discussed, and we have to make sure that the component of angular momentum along the internuclear axis, that is this one, is conserved. The other selection rules, there are two more selection rules which concern the symmetry, changes in symmetry, and this for if it involves sigma terms, we've discussed in the last class that these two are the valid uh, valid transitions if sigma plus to sigma plus and sigma minus to sigma minus. And this was because we now understand that under reflection symmetry, the z component of a dipole moment operator remains unaffected, behaves as an even function, and that's why we have this kind of rule coming up for this. Laporte selection rule is already well known to you. You have been studying it since your class 12 first semester. We have already discussed. So G to U to G transition, again it is the consideration that the integral that we are looking at must be an even function overall, and that's why uh, so when you are looking at center of symmetry and performing the inversion operation, all these um, xyz component of the dipole moment behaves as odd function, and so to make overall integral even, you have to make this thing when we are talking about psi f, mu, cap, and psi I. So this integral, the transition dipole moment, this is given by this integral, and this must overall, this function has to be even, then finite value. If this integral is odd, then it becomes 0. That's what we try to make out when we are working with. So this is when we try to make out even the overall function as even, so that it has net transition. We find that if u goes to g or g goes to u, that kind of transition will be having a net transition dipole. In other cases where it turns out to be odd, the multiplication, that is the case of g to g, u to u transitions, that is this transition dipole becomes 0, and so nothing will happen. So these are things that we have already discussed. I'm not going into this again. You can see the last few lectures, which I think I have recorded, and I'll share it soon. And so vibronic coupling, that's when the symmetry is momentarily broken, then G to G and U to U transitions can occur, and you get a weak signal corresponding to those things. So that's, we also call them vibronic. So vibration plus electronic becomes vibronic. Okay, so when we say vibronic, it is sum of vibrational plus electronic vibronic transitions. So it is because of the removal of central symmetry momentarily which makes it happen. Otherwise, strictly speaking, if the molecule is static, not undergoing vibration, G to G, D to D, GG transition or UU transition won't happen. Then we considered this. We had discussed the transitions involving sigma plus to sigma minus, and we again find that the function becomes odd if we take because the z component behaves as even function here, and so these transitions are not allowed. And the only one that amongst the given in the among the transitions given below, only this one, the last one, is allowed. Rest is not allowed. Why it is not allowed? You can see either spin angular momentum or orbital angular momentum is not being conserved. And so just like we were seeing in this vibrational spectroscopy, that if you look carefully there will be lines associated with the PQR. In the PQR branches of the vibrational spectra you will get uh, very fine lines. That was rotational fine structure, so that corresponding to the rotational transitions. Here in an electronic spectra you see this kind of uh, zigzag, this spiky things. The spikiness that you see is due to the spikes that you see is associated with the vibrational transition from the ground vibrational state in the ground electronic state to the and the different vibrational states of the electronically excited state. So that transitions is appears uh, as a superimposed transition on the basic electronic transitions, and that's how we get these spikes. So this is just typical of gaseous SO2 at 290. So look at the y-axis. Y-axis is this. Look at the x-axis. This is the lambda. So and on the y-axis it is the epsilon, the molar extinction coefficient. So these sharp lines that we see, which are superimposed on the top of the absorption spectrum, these are the what we know as vibrational structure in the electronic spectra. So Frank-Condon principle that we considered, we learned last time. It is the nuclei which are much heavier. They have greater mass as compared to electron, and so they do not move when the absorption of photon occurs and electron moves to the higher electronic state. So that is the essence of this Frank-Condon principle, that you visualize the two nuclei as static because the process of electron movement is 1000 times faster, and so that because of that difference in the time scale we can say that it is a vertical transition that occurs between two stationary states, when the nuclei are assumed to be stationary, and that what was the central mean position earlier, equilibrium position for the vibration, now becomes a terminal position, the turning point for the new vibrational state in the new excited state, electronically excited state. So these are the points that we look at, and we found further that it can be further explained through the concept of quantum mechanics, where we have to look for the transition moment integral that was coming out to be, yeah, when you have a good overlap of psi f and psi I. So that was the key thing. So if you have, so suppose the electron was here when the vibration was taking place. It was at the mean position. So if you analyze all these things, v is equal to 0, v is equal to 2, like that, we find that the for v is equal to 2 state, at the same vertical line, if we draw the uh, the profile of the the wave function is exactly the same. It is having highest amplitude at this point, and so overlap will be good between the two wave functions, and you will have a very high value of the transition dipole moment, and it will be the most intense lines. So how to identify the most intense vibrational transition which gets superimposed on the top of electronic spectrum is this one, that will be now the terminal position, and so you can see that you are dealing with a higher ground vibrational transition of electrons from the ground vibrational state to the ground electronic state to the upper electronically excited state, and in the process you are having excitation of the vibrational levels. The vibrational level which is having the similar profile of the matching profile of the wave function in the upper region, that is the one which is going to have highest transition dipole moment. So that will be more intense line. So a good interaction with the photons, you can expect a higher value of the absorbance. Okay, so that is the idea, we get it. For other transitions will also for other points the transition may happen, but the overlap will not be that much that good, and so that those will be always a weaker signal. So v is equal to 1 is possible, v is equal to 3 is also possible in the transition, but they will have poorer overlap of the two wave functions. And so we have the third line in the vibrational thing. This v is equal to 2 state is the most intense. So that's why we say that it is the one which resembles upper vibrational state, that most closely resembles the vibrational wave function of the ground state, has the maximum value. See, so we are assuming the electrons to be moving much faster. They are lighter around by a factor of around 2000 times less massive as compared to protons, neutrons, and so it is when the light is absorbed, it is the electrons which move very fast within few femtoseconds, while the nuclei remains almost there in their position. And later on, when what happens is that the electronic arrangement has changed, and so the vibrations the arrangement changes, so electric field around the nuclei has also changed, so they will rearrange to a new equilibrium position, and that is, you see here, the mean position is here. Now it is vibrating about a different mean position as compared to the previous case. Equilibrium bond length has changed now in the exact electronic state as given in the picture. So this is what we call as the most probable location of the nuclei at the equilibrium separation, Re, because you have maximum value of the amplitude squares give you the so this is ground state vibrational wave function behaves like this, have maximum amplitude, and square of amplitude gives you this probability electron density, probability density, and so that's how we try to identify it, the position which the transition which is the vibration transition corresponding to this, which we will have maximum signal. So Re means Re equilibrium, So electronic transition occurs. Molecule is excited to the new upper electronic state, which is the new potential well, upper curve, and according to the fan quantum principle, the nucleus doesn't move, and so it remains in the position as it is only. And so the transitions are to be represented through a vertical line that we have drawn, and we also call it sometimes vertical transition. So this word vertical transition originates because if we draw it in this way, only then we can understand what is happening with the system. Okay, so electronic transition occurring without the change of nuclear geometry, that is your vertical transition. So it may happen through several vibrational levels of upper electronic states. Uh, so we have seen the maximum amplitude of the one labeled with star is having maximum vibrational wave function with maximum amplitude, and that is exactly having the same position as the lower one, which is, so similarity of the two profiles gives you the best transition dipole moment. So this is an essential criteria. If there's huge dissimilarity, if something is zero, then you multiply the two things, it will become zero. So they are present at RE position as in the ground state. So electronic vibrational state, sorry, so the vibrational state is most crucial state for termination of the transition. That's okay. So we have understood this point, that so the vibrational wave function that peaks most strongly near RE, so corresponding to this equilibrium bond length, that will have most very good transition, very good absorption of light will happen. So it is the, now we are analyzing a hypothetical situation where you have two situations, one in which the ground state and the excited state, ground state and excited state, okay, they are non-displaced. Just for a moment, let's assume that if they are not displaced, excited state is having same position of the potential well, that is the equilibrium bond length is almost the same as this one. This is scenario 1, and the other scenario is more realistic one, where you have, it is the potential well is shifted. So you can see here that it is the minima is here, which is shifted one, and but in this case, so this is a case of non-displaced uh, electronic excited states, and the results are similar to what can be expected for this system. Uh, so there are two situations. If the potential energy curve is appreciably displaced, the first, this one, it is displaced. The upper curve is usually displaced to greater equilibrium bond lengths. Uh, so when you are putting electrons from the ground electronic state to the next electronic state, you are gradually having putting the electron in a orbital which has more anti-bonding character. So it makes sense that sometime if we as can, so because if there is anti-bonding character, that will, there will be some repulsion between the nuclei and they will be pulled away. So usually, so the drawing of the top one is the most likely case that happens in a electronically excited state. Okay, so this separation of vibrational lines depends on the depends on the vibrational energy of the upper electronic state. So upper electronic state will have vibration which might be slightly different from the ground state vibrations. Okay, the situation has changed now, and they will be likely to be more repelled by this. Um, yeah, sorry. So, so the displacement. So, if you are observing very carefully the vibrational lines, separation of the vibrational line give you a lot of information, important information through this electronic absorption spectrum. Because starting from the ground vibrational state, so this is the ground state of the vibrational state, and from there you are achieving all the different transitions. So an absorption spectrum will show a very good progression of lines. You will see a lot of lines superimposed over the fundamental electronic spectra that corresponds to different vibrational transitions. So once, as I told you, it is a vertical transition. The nucleus position has not changed at the time of absorption of photon, but soon after that there will be some rearrangement because there is the electromagnetic force around the nucleus has changed, and so the nature of curve will change. So that can be used if you analyze this well. You should be able to find the dissociation energy for a particular molecule in the excited state. Yes. So the transition dipole is usually this is the shorthand notation for the integral that we discussed. So this is something you must remember what we mean by this, writing in shorthand notation. Mu fi is nothing but integral psi f mu mod, that is the mu cap and psi I. So this was the thing that we were discussing while describing transition dipole moment, and this is the shorthand notation. When you write this whole thing, it is this the same thing describing this. Okay, so remember how to write the shorthand notation for the integral like this. So now we are going to define that, yes, from Frank Condon principle we have understood, but now we are going to quantify it mathematically. We can calculate how much is there is going to be, uh, how many photons, what is the absorption rate of photons by the system, whether it is good absorbing properties or not. So that is determined by Frank Condon principle. Frank Condon factor we are going to calculate. So the dipole moment operator, you have to look for all the electrons, their positions. Similarly, you will also look for the protons in the nuclei. So all of them together, the summation of which will give you the total dipole moment. So dipole moment is the calculation involving electronic part, and this is the nuclear part. So nuclear part. So position of nucleus you have protons. So basically these are the location of these charges with respect to a well defined origin. Okay, you can calculate it. So this is the how we write the expression for protons and electrons and their angular momentum. Sorry, not angular momentum, the transition dipole moment. So usually what we have learned through the Born-Oppenheimer approximation, electronic part does not depend on nuclear positions. Okay, the transition dipole moment, basically, if we start writing, so using this concept, we write extra all the terms. So involving these terms, you can see the electrons with different I values. So all these sisters and so yeah, sorry. So this is the total values that you can see, and then so you have the total wave function. We are looking at the total wave function, the final state. So epsilon I f and v f, and then we have epsilon y and mu I. Sorry, it's not v, it's mu I. So initial wave function for uh, yeah. So these two things you can clearly see, and this is the operator mu. This is what this entire thing that you see is the mu, the operator, as operator that we written over here. So expand these terms, it will come out to be two things. So you have a psi f psi I term, then you also have this term. This second term is because any two functions, when you are looking at electronic wave function, electronic wave functions are always orthogonal, so this product is going to be 0. Electronic wave functions are orthogonal, so this is going to be 0. So this happens to be 0. Second term you can omit. So second term is going to be 0 because of the two electronic states are orthogonal. Now your equation becomes simpler. Equation how it, so it only the first term is to be considered, which involves the electronic wave function and then overlap between these two. So sorry, this Ri and the vibrational wave function like this. So together this whole thing we can write like, sorry, so this thing, this term is going over here. This entire thing is the typical dipole moment, and this second thing that we see here, it is coming into this. The capital S that you see, which represents the shorthand notation for the overlap of the two wave functions, corresponding to Vf and Vi, initial and final vibrational states in the two electronic states. So this particular thing is very important. Okay, so we have clearly written this thing. So this thing is basically, we are considering this particular integral is what we are writing in a shorthand notation, Vf Vi. So this is the vibrational thing. So this is vibrational integral involving vibrational wave functions. Moving ahead, so mu Fi that we were considering, that this mu Fi, so the same thing, the electric dipole arises from the redistribution of electrons, and a measure of this we have discussed last time with an example of S and P orbital transition and S and 2s transitions. So that mu Fi is the new electron dipole transition moment. The electrons are redistributed, charges are redistributed, electron field will also change, and so this is the overlap integral between the vibrational state with Vi, initial one, electronic state and vibrational state with EF. This is the final electron state of the molecule. And the square of this term, remember, look at this, please सोइएगा नहीं. This is the Frank Condon factor. The square of this integral term, taking mod of that and then taking square, gives us the Frank Condon factor for the transition. So Frank Condon factor is a good thing to know. If you know this, you can predict the intensity of the signal when you are doing this electronic spectroscopy. Okay, so this is for, so we'll have more discussion on that. So intensity of remember, the intensity of transition is proportional to the square modulus of the dipole that is being developed, mu fi. So psi f psi I with this. So that determines the magnitude of transition dipole moment. Okay, so this intensity is proportional to the square modulus of overlap integral that we have just discussed. So, so overlap integral, so what we have Vf and Vi, we are writing the two vibrational wave function, and if the match is good, match between the vibrational wave function in the upper and lower electron state is good, this S value sorry, there was phone. Okay, so important thing is that कि हमने एक इंटीग्रल वाइब्रेशनल वाला सेपरेट करके एस वी एफ ऐसे डिनोट कर रहे हैं हम इसको. Oops, sorry, just fall. So this is in case of maximum overlap. This capital S will be equal to 1 for perfect match, and when there is no similarity, the S will be equal to 0, and that is the situation where you don't have transition dipole will become 0. So greater the overlap, the vibrational state function in the upper electron state, in the lower state they have good, if they have good overlap, there will be good absorption intensity. The absorption signal in the spectrum will be good, very good. And if there is no match, then it will be 0. So these are the two things that we observe in this electronic spectra of electronic spectrum of any molecule or something like that. Okay, so so the greater the absorption, so greater is the overlap, greater will be the absorption intensity. So these are the word to be picked up if you are looking at greater the overlap. So overlap of what? The vibrational wave function in the ground electronic state and the upper excited electronic state. So दोनों में जो wave function है vibrational wave function है, उसका जितना अच्छा overlap होगा उतनी ही अच्छी तरह से आपको absorption signal मिलेगा. So there will be, or you can say that it will be more intense. Absorption signal is more intense. So this is the conclusion. So this is what we had pictorially described in the previous slides. In the previous slides, where we found that vibrational wave function of ground state has greatest overlap with the vibrational states. So matching of the profile of the wave function in the vibrational state of the ground electronic state and the excited electronic states. That's what we were doing, and we have already analyzed situations like this. So good overlap and maximum intensity of the absorption signal will be seen. Okay, So this is a situation where, so usually this is the kind of situation that we have, that the upper electronic state is slightly displaced. It is displaced from the, as compared to the ground electronic state. So you can see the central position. This is here. It is ground state, excited state, ground state, equilibrium position, and this is the excited state, equilibrium position. So clearly you can see the difference is there, and this difference can, so what is the, depending on the difference in this situation, how close or how far it is, this we can have, that will affect the vibrational transitions, and the lines, the number of lines that you can see in the spectrum. So that will vary with respect to how much is the upper electronic state is displaced from the ground electronic state. So we will see, we will have a discussion on that. So this is the same situation described through this picture that was, you can see. So if the molecule is in the central position, it has maximum overlap with this one. If the molecule happens to be in this vibration state at this particular internuclear separation while vibration, it will have best overlap with this one, and so on. So these are three lines that has been drawn to represent three different best cases. So under the different cases of vibration, so vibrational position is the mean. If the molecule happens to be at the mean position when the photon comes, the second arrow is the thing that you look at. If it is slightly left or right to the mean position, it will have good overlap with this particular vibrational wave function, and so accordingly the transitions will be observed. So this is what to be seen and observed. So we are discussing the excited state which are displaced as compared to the ground state, excited state, excited state. So Frank Condon principle is just, so what you can expect in this is the spectrum that we see, absorption spectrum, absorbance, and what you are seeing here, wavelength as this, and then these are the transitions. So this is the different vibration quantum number V, this is V prime, V, V prime, and so on. So I mean the first, for the ground state, this corresponding to the ground state, ground state, and this is the excited electronic state, like that, 0 to 1, 0 to 0, 0 to 1. So 0 to 0 we mean this one with this one, 0 to 0. So so this can happen. So this is of very low intensity because the overlap is not good. When we draw a straight line, we find that when we start here at 0 to 0, the overlap is very less. But when we are looking at this picture 1 2, 0 1 2, v is equal to 0, ध्यान से देखिएगा, v is equal to 1, v is equal to 2. अब आप ध्यान से देखिए, सबसे अच्छा ओवरलैप किसके साथ हो रहा है यहाँ पे, v is equal to 2 स्टेट में जो है मैक्सिमम एम्पलीट्यूड है, और यहाँ पे जो ग्राउंड स्टेट में वाइब्रेशन v is equal to 0 स्टेट में है maximum amplitude. So the overlap, the matching, sorry, it is very well matching with the excited state wave function, vibrational wave function v is equal to 2, matches very well for this particular position, equilibrium. So 0 2 वाला transition most intense आ रहा है, most intense. So you are having most intense transition for this particular thing, है ना? बाकी सब के लिए इसी पोजीशन से रहते हुए, सॉरी मैं बार बार टच कर दे रहा हूँ। सो इसी पोजीशन पे रहते हुए जब आप इस पे देते हैं तो v इक्वल टू जीरो वाला, तो इसमें देखिए बहुत कम, इसका एम्पलीट्यूड यहाँ पे ज़्यादा है ग्राउंड में, ग्राउंड स्टेट वाले वाइब्रेशन फंक्शन पे यहाँ से कम है, तो ओवरलैप बहुत पुअर होगा। तो जीरो टू जीरो वाला जो ट्रांजिशन है उसके लिए इंटेंसिटी बहुत कम होगी, जीरो इन द ग्राउंड स्टेट टू जीरो ये द एक्साइटेड स्टेट, तो इसकी इंटेंसिटी बहुत कम आ रही है। जीरो टू वन पे थोड़ी सी ज़्यादा, but best case scenario is 0 to when it goes from 0 v is equal to 0 to v is equal to 2 in the eccentricity। यहाँ पे ये वाला जो है बेस्ट केस सिनारियो है, बहुत अच्छा ओवरलैप होगा, सो मैक्सिमम ट्रांजिशन यू कैन सी। उसी तरह से उसके बाद भी अगर आप कोई कंसिडर करेंगे, एरो को ऊपर उठाते चले जाएं, यहाँ पे भी आप देखेंगे कि एम्पलीट्यूड कम हो गया, तो अगेन देयर इज अ डिक्रीज। सो आइदर साइड ऑफ 0 2 line you can see there is decrease in the intensity of the signal, absorption signal as seen in the spectrum is decreasing on either side of this 0 to 2 transitions. So this is a normally this is what we encounter for most of the molecules, सारे के सारे नहीं लेकिन मैक्सिमम केसेस में यही होता है। इसी तरह का डिस्प्लेस्ड इलेक्ट्रॉनिक और ग्राउंड स्टेट होता है, electronic ground state, electronic excited state is displaced like this, and then you can have this kind of vibrational lines appearing on this. Now imagine another case, suppose we have an electronic excited which is non displaced, उस केस में क्या होगा? तो अगर आप जीरो से स्टार्ट करेंगे सपोज यहाँ से, तो इसका बेस्ट केस सिनारियो यहीं पे आएगा, मैचिंग, बाकी किसी के साथ अच्छा मैच नहीं आएगा, जीरो जीरो वाला यहाँ पे मैक्सिमम हो जाएगा। So, अगर आपके एब्जॉर्प्शन सिग्नल स्पेक्ट्रम आप देखते हैं और जीरो टू जीरो ट्रांजिशन वाला मैक्सिमम आता है in terms of vibrational, so this is the v to v prime, so you can see that if this is the showing maximum intensity, that means the, so आप एब्जॉर्प्शन स्पेक्ट्रम देख के प्रेडिक्ट कर सकते हैं कि किस तरह का पोजीशनिंग होगा दोनों जो इलेक्ट्रॉनिक स्टेट्स है, ग्राउंड स्टेट एंड एक्साइटेड स्टेट, whether they are displaced or non-displaced. Just looking at this spectrum, if 0 to 0 is most intense, that means ground state and excited state are at this, have the same internuclear separation, equilibrium separation. Okay, so these are two extreme situations जो हम इमेजिन कर सकते हैं। हालांकि मैंने जैसा पहले कहा कि इन मोस्ट केसेस यू विल इनकाउंटर दिस काइंड ऑफ द डिस्प्लेस्ड excited state is the most common one, but in very some very specific cases we will have this kind of also. So now we can quantify this thing. Let us consider transition from one electronic state to another. The bond length changes Re to Re prime, so actually it is subscript which I have not been able to do it. Put थोड़ा सा typing error है. And suppose their force constants are equal, bond lengths are given, calculate the Frank Condon factor for the 0 0 transition and show that the transition is most intense when the bond lengths are equal. Okay, so equilibrium bond length जो हम जिसको कहते हैं, तो that is, so we are trying, वो जो चीज़ हमें ऐसे फिगर से पता चल रही है उसको हम थियोरेटिकली कैलकुलेट करके दिखाने जा रहे हैं कि वो फ्रैंक कॉन्डन फैक्टर का वैल्यू क्या होगा और इसलिए इंटेंसिटी पे क्या असर पड़ेगा। सो लेट अस कैलकुलेट S00, द ओवरलैप ऑफ what is this? This was psi VF and psi, so वाइब्रेशनल वेव फंक्शन का VI इनिशियल और फाइनल, जब ये भी ज़ीरो है और ये वाला भी ज़ीरो है, वी आई वी एफ दोनों जीरो है, तो ये वाली सिचुएशन। तो इसको हम लोग ओवरलैप इंटीग्रल को इवेलुएट करने जा रहे हैं। टू ग्राउंड स्टेट वेव फंक्शन एंड देयर square, that will be, if we take the square, that will be the Frank-Condon factor. So overlap integral of the two vibrational functions and taking the square, that is how we that completes our evaluation. So let's look into this. This is the basic idea we will start thinking about कि कैसे हम इसको रिजॉल्व करेंगे, सॉल्व करेंगे। तो ये चीज़ यहाँ से आप सोचना शुरू करते हैं। So for v is equal to 0 state, one more thing that you can simplify your calculations is that the behavior between the difference between harmonic and anharmonic vibrational wave function is negligible. It is almost a simple Gaussian function, Bell type curve that we observe for, and it is not much affected by the anharmonicity. We have all seen this thing. When we increase the quantum number, we find more and more uh, greater effect in the difference in the wave function profile. So whether it's harmonic or enharmonic, v is equal to 0 is almost unaffected. Very small change is there. So we can make some simplification that simplifies our calculations. So psi naught. So when we can calculate. So looking. So we in the last class, last semester actually, while discussing the simple harmonic motion, the simple harmonic oscillator, we had discussed the functions, that this kind of function is the one that describes the behavior, and so it is the initial in the ground state, and then we can define another one in the excited state. Okay, and so x, so here the x that you see is the r and r minus, so displacement, so this x is the displacement, right? And this is the equilibrium position, equilibrium distance, equilibrium bond length, you can say. So the distance between the two nuclei when they are at equilibrium position, equilibrium position of the vibration. So that is the called displacement. X prime is the displacement in the when the vibration is taking place in the electronically excited state. So you have a new Re prime. This is a new equilibrium bond length in the excited state. And so we are comparing with this understanding, we can compare. So you can see the term, this is for excited electronic state, this is the ground electronic state. So this x prime is x and x prime. Now you understand how it is defined. Equilibrium bond length may be different, it may be same, but here the case that we are discussing, that we are trying to evaluate this is when the equilibrium bond lengths, how when the function overlap will be maximum between the two wave functions that we are considering, and the overlap integral. So overlap integral can now be calculated. Simply substitute the two values of wave function and integrate it in the limit minus infinity to plus infinity. So substitute the values and you get an expression something like this, x square. So दोनों वैल्यू ऊपर दी हुई हैं, दोनों को सब्स्टिट्यूट करना है, and you get exponential function minus x square plus x prime square divided by 2 alpha square. So continuing from there, we started evaluating this thing, and we write alpha z as another term, which will be representing this r minus half re, so half of the, so this is the difference between the equilibrium bond length This is also equilibrium bond length. What is the difference? दोनों में डिफरेंस क्या है? दोनों इक्विलिब्रियम बॉन्ड लेंथ को एक एक्साइटेड इलेक्ट्रॉनिक स्टेट में, हाँ ये ग्राउंड इलेक्ट्रॉनिक स्टेट का इक्विलिब्रियम, और ये एक्साइटेड वाले का है, एक्साइटेड इलेक्ट्रॉनिक, ये डिफरेंस। सो उस पॉइंट को ले रहा है एक्साइटेड इलेक्ट्रॉनिक स्टेट। सो नाउ थोड़ा सा मैथमेटिक्स को सिंप्लीफाई किया था जब ये एक और एडिशनल फंक्शन हम अल्फा जेड डिफाइन करते हैं, और दैट इज टू सिंप्लीफाई लिटिल बिट। सो व्हेन वी सब्स्टिट्यूट दिस, यहाँ पे जो एक्सप्रेशन है ये सारा देखिए कैसे सिंप्लीफाई हो रहा है, एक्स स्क्वायर, सो व्हेन वी put it like this, alpha z in these terms, then this z comes to e to the power minus z square dz के टर्म में इंटीग्रल में आ गया, और बाकी all other things are constant. So re prime, that is known, only variable e to the power minus z square, this becomes the only variable, and so it becomes easy to understand the how this whole overlap integral will behave. Simply look at this z square value. So the value of integral is pi half, uh, pi to the power, sorry, under root pi, that is the value if overlap integral is then given by this is the integral. So Frank Condon factor is simply this, in this case e to the power. Now if suppose, so equilibrium bond length, these two things are equal, then it will have, for 0 to 0 transition, it will have maximum value. आप रख के देखिए. So this factor that we are considering, this is the expression, right? So it will be equal to 1 when re prime is equal to re, and it will go on decreasing as the equilibrium bond lengths diverge from each other. So when the two potential well, excited state electronic state, ground electronic state, they are positioned in the same way, मतलब इक्विलिब्रियम बॉन्ड लेंथ मीन पोजीशन दोनों में सेम है, उस केस में बॉन्ड लेंथ ये दोनों का सेम होगा, और उसी 0 0 वाली ट्रांजिशन मैक्सिमम आएगी, जो जो ऑब्जर्वेशन था पीछे पिछले की स्लाइड पे, उसी को एक्सप्लेन किया जा रहा है. So the Frank-Condon principle for considering 0 0 transitions in the vibration level, from we find that it is maximum when, so this is the internuclear distance, uh, so when this function is 0, it is having maximum value, and anything, so as they are displaced gradually, जैसे जैसे डिस्प्लेसमेंट बढ़ रहा है वैसे वैसे ये वैल्यू कम होता जाता है, इंटीग्रल कम होता जाएगा. सो 0 0 ट्रांजिशन जो है, it is maximum when the two are, so that is what we have just seen through pictures in the previous slide. देखिए मैं वापस जा रहा हूँ, non displaced, it will have maximum value when you are having no displacement of the two, uh, sorry, hello. हेलो। या हाँ, तो मैं यही कह रहा था कि जो हमने यहाँ पिक्टोरियली समझा था उसी चीज को मैथमेटिकली अच्छा शायद शेयर नहीं हुआ। ओके सॉरी, स्क्रीन हैज नॉट बीन शेयर्ड। ओके ओके सॉरी सर। बीच में सिग्नल उड़ गया था। हाँ, I realized that the signal was lost for some yeah, my network was off. Okay, so what we were discussing in the previous slides through pictures that we are trying to quantify and find out, show this thing as a through the Frank Condon calculation of the Frank Condon factor. So yeah, so these two are the contrasting pictures, displaced and non-displaced one. So what we understand by now is that when it is a displaced one, we always have a highest transition at some different uh, vibrational quantum numbers as compared to the, so 0 to 2 here that you see. But if you, for non-displaced excited state, that is there is no change in the bond length, that's what we interpret it. When the bond lengths are equal, तो बार बार लगाएंगे। ओके, सो बहुत दो कॉन्ट्रास्टिंग पिक्चर को हम डिस्कस कर रहे थे। ओके, ये क्या हो गया? हाँ, अभी कट जा रहा है नीचे। Okay, so 0 to, so this is always the case for any displaced case, there will be slightly different. So the maximum signal will be obtained for, if you are starting from the ground vibrational state of the electronic ground state, so 0 to 2 is the maximum. मतलब ऊपर वाला हायर क्वांटम वाइब्रेशनल क्वांटम नंबर पे होगा ट्रांजिशंस, मैक्सिमम वैल्यू वहां पे होगी। Whereas if it is non-displaced situation, that is displaced, we are looking at the position of the equilibrium position, दोनों का लगभग सेम है, उस केस में 0 0 वाला मैक्सिमम। The same thing we try to understand through calculation of the overlap integral, and when it is compared, we find that the maximum value of the integral is obtained when the two distance it is equal. That is, for 0 0 transition, the Frank Condon factor is maximum. It is equal to Frank Condon factor is 1 when both the bond lengths are equal. That is, the two potential well are placed at the same position, and so we have maximum here, maximum value, and it gradually goes on decreasing. So this is the this factor which is plotted here. So you have this kind of thing. So you can clearly see here that as a situation where you have this difference in the distances between difference in the equilibrium bond lengths of the two electronic states. So if there is any difference, if the two electronic states are displaced with respect to each other, then there will be decrease in intensity of the this as the displacement increases. 0 0 by transition shows less and less intensity, and finally it is very less at a certain value that is shown over here. So the similar thing that so now we have discussed this the effect, how we can interpret the vibrational fine structures observed in the electronic spectrum using the Frank-Condon principle. We have also learned how we can evaluate the Frank-Condon factor, which is the overlap integral, square of the overlap integral. Okay, square of the overlap integral is the Frank-Condon factor, is the this thing square of the integral. And 0 0 means this is the vibrational transition, v initial, v final, v prime for the several states, and it goes on decreasing. That's the calculation that we have. So in vibrational spectroscopy earlier in we found rotational we found that vibrational transitions were accompanied by rotational excitations. Now what we are seeing here that uh, electronic spectroscopy spectra is associated with vibrational transition, and so each of these vibrational transitions will also be having some rotational accompanying rotational transitions. Okay, so overall thing will be that you will have इलेक्ट्रॉनिक एक्साइटेशन, उसमें वाइब्रेशनल भी होगा, और हर एक वाइब्रेशनल के साथ रोटेशनल ट्रांजिशंस भी होंगे accompanying the vibrational excitation. Okay, so few things will be observed in rotational fine structure. Something can be seen sometimes in the electronic spectra. PQR, so electronic transitions. So PQR branches for each vibrational transition, and the electronic transition has very rich structure. Uh, I think I can continue here the rotational fine structure in electronic spectra in the next class, and I will take it tomorrow morning at 6:45 AM. कल हम लोग सुबह में इसको डिस्कस कर लेते हैं. अभी जितना बताया उतना आप ग्रास्प करने की कोशिश करो. You just try to learn what has been discussed today, and then we can continue from here, and we can learn more about these things. Okay, so